Hello and welcome back to another video. In this problem, we're asked to explain using theorems 4, 5, 7, and 9 why the function is continuous at every number in its domain. We're also asked to state the domain. So the first thing we're going to do is we're going to consider the fact that this isn't just cleanly a function that we know, right? So what we're going to do is we're going to split this up into different functions. We're going to say we have a of x is equal to the square root of x, b of x is equal to 1, and c of x is equal to 1 over x. And this is going to be equal to m of x. We're taking the square root of something, so this is a of something. What is inside? It's not an x, it's 1 plus 1 over x. So it's b of x plus c of x. So we know from theorem 7 that certain numbers are continuous over their domains, which is what we're trying to see for this overall function. So a of x is a root function, 1 is a polynomial, and c of x is a rational function. We know from theorem 7 that all of these types of functions are continuous over their domains. Therefore, b of x plus c of x, which we can call, d of x, which is 1 plus 1 over x, by theorem 4, which states that if you're adding two functions and they're both continuous at a point, their sum is continuous over that point. And then we use the fact that we have theorem 9, which states that for a function f of g of x, right, if a value a is within the domain of g, so g of a exists, and f of g of a exists, right? So a is in the domain of g, and g of a is in the domain of f. If both of those things are true, then f of g of a is continuous, right? It is continuous at this point a, right? And this is theorem 9, based off of the ways that they're asking us to do this. Therefore, b of x plus c of x is continuous over its domain. A of b of x plus c of x is continuous over the domain of b of x plus c of x. And, it's continuous over the domains of b of x and c of x and a over b of x plus c of x. And therefore, because this is the exact way we find the domain of M in the first place, M, as a combination of those things, is continuous over its domain. So what is the domain? Well, we have a couple of restrictions here. The square root of x has a domain restriction in that what's inside cannot be less than 0, right? So we're not finding the square root of x being less than 0 because we're taking a of b of c of x, right? So it's not f of a is a domain restriction, it's f of g of a. So let's start with b and c, since those are the things inside a. Polynomials don't have any domain restrictions. Rational numbers do. Their denominators cannot be equal to 0, so x can't be equal to 0. And then we take them together and say 1 plus 1 over x has to be greater than 0, right? And if we therefore take 1 over x has to be greater than -1, then we can simply say that we know that we have this function 1 over x, and x can be greater than 0, and this is true, or x can be between 0 and the value for which 1 over x dips below -1, which is itself -1, right? So the domain restrictions is basically that x has to be greater than -1, but it can't be 0. However, we already knew that x can't be 0, so that doesn't even matter. And we can therefore say that m is continuous over its domain, which states that x has to be greater than -1, and x cannot be 0. If you're wondering how I found the domain based off of this, you'll have to graph the function of 1 over x. That's the easiest way to do it.